Fine. Let's start. Here's the problem with big numbers. When someone tells you the universe is 13.8 billion years old, you nod. You feel something. You think, okay, that's a lot, but you don't actually feel it because your brain is doing what it always does with numbers that size. It rounds them off into a vague sense of very big and moves on. And honestly, that's fine. That's the only thing a human brain can do. But what happens when the numbers get so large that even the concept of very big stops working? What happens when you leave behind billions and trillions and start dealing with timescales so extreme that the age of the universe doesn't even register as a rounding error? That's what this is about. These aren't just large numbers. Some of them are large in a way that quietly breaks the framework you use to understand anything at all. Number 10. Our planet has a second clock. Not the one that measures days, not the one that counts years, a much slower one. The solar system, our sun, our Earth, every planet in between, is orbiting the center of the Milky Way galaxy, right now, at roughly 828,000 kilometers per hour. And one full lap takes approximately 225 to 250 million Earth years. Astronomers call this a galactic year, or a cosmic year. Earth has completed about 20 of them. Let that settle for a second. 20 orbits around the galactic center since the planet formed. And here's how you feel what that means. The last time Earth was at this exact position in the galaxy, the Triassic period had just ended. The first dinosaurs were taking their first uncertain steps. Go back one more orbit, one galactic year earlier, and complex multicellular life had barely figured itself out. Single galactic years erase everything we think of as ancient history. Dinosaurs, the entire Mesozoic, the rise of mammals, all of human civilization. That's all 1/5 of a cosmic year. 1/5 of one lap. We think of our address in the cosmos as fixed. The Milky Way, the solar system, Earth, here. But here is not a location. It's a moment in a very long loop. And right now, at 828,000 kilometers per hour, we are somewhere in the middle of lap 21. Number 9. About 600 light years away, in the constellation Auriga, there's a planet called WASP 12b. It's a gas giant, roughly 1.5 times the mass of Jupiter, and it completes a full orbit around its host star in just 26 hours. For context, Mercury takes 88 days. This planet is so close to its star that it's being stretched into something almost egg-shaped by tidal forces. And it is dying. Not dramatically, not quickly, slowly. The kind of slow that makes 3 million years feel like a countdown. A Princeton-led team confirmed in 2019 that WASP-12b's orbit is decaying. The planet is spiraling inward, millimeter by millimeter, year by year, pulled toward its star by tidal dissipation. In roughly 3 million years, it will be consumed. The way they confirmed this was by measuring the time between successive transits, the moments when the planet passes in front of its star. Each transit was arriving 29 milliseconds earlier than the last. 29 milliseconds. Less than the duration of a single camera shutter click. That was the evidence. That tiny, repeating shortfall, accumulated across 12 years of observations, was enough to confirm a death sentence 3 million years in the future. Here's the thing about 3 million years. It sounds enormous, and by any human standard, it is. 3 million years ago, our ancestors were still figuring out how to use stone tools. But on cosmic timescales, 3 million years is nothing. It's the fastest orbital decay we've ever measured. Most hot Jupiters like WASP-12b spiral in over billions of years. So slow we'll probably never confirm it's happening. WASP-12b is the rushed version. Somewhere out there, an egg-shaped planet is counting down. It just has a very long count. Number 8. The most common type of star in the universe is also the dimmest, the coolest, and the most miserly with its fuel. Red dwarfs make up roughly 70 to 75% of all stars in the Milky Way. They burn so slowly, so carefully, that the smallest ones are expected to live for 10 to 12 trillion years. That's 10 to 12,000 billion years. The universe is currently 13.8 billion years old. So a small red dwarf born today is looking at a lifespan roughly 700 times longer than the current age of everything. But here's the thing that makes this genuinely strange. Not a single red dwarf in the universe has yet died of old age. Not one. The concept of a dead red dwarf, a helium-white dwarf produced when a red dwarf finally exhausts its hydrogen, is entirely theoretical. Astrophysicists have models for what it looks like. They've done the maths, but no one has ever actually seen one because the universe has not been around long enough to produce a single example. Every red dwarf that has ever existed is still alive, still burning, still in the first chapter of a story that hasn't reached its second yet. We have detailed stellar evolution models for an event that has never happened anywhere in the observable universe. Ever. And here's the implication that usually goes unspoken. The universe's star-making story, the long, slow era of fusion and light and warmth, has barely begun. We are living in what cosmologists call the stelliferous era, the age of stars. It started a few 100 million years after the Big Bang and will continue for about 100 trillion years. We are currently 0.014% of the way through it. We are so early that the words early universe are genuinely accurate even now. 13.8 billion years in. Most of what the universe will ever do with stars hasn't happened yet. The best is probably still to come, which is either comforting or terrifying, depending on your mood. Number 7. In 1974, a PhD student named Russell Hulse was working with his supervisor, Joseph Taylor, using the Arecibo radio telescope in Puerto Rico. They found something unusual. A pulsar, a rapidly rotating neutron star that was behaving oddly. Its pulses were arriving at irregular intervals, speeding up and slowing down in a very specific, periodic way. The reason turned out to be that this pulsar had a companion. Another neutron star, orbiting it so closely that the two were locked in a gravitational embrace, circling each other every 7.75 hours. The first binary pulsar ever discovered. They called it PSR-B 1913 plus 16. And they kept watching it. Over the following years, they noticed something. The orbit was shrinking. Not by much, just 3.5 meters per year. Less than the length of a car. But the shrinkage was perfectly consistent, year after year, and it matched exactly what Einstein's general theory of relativity predicted for a system losing energy by emitting gravitational waves, to within 0.3%. This was the first indirect confirmation that gravitational waves were real. Hulse and Taylor won the Nobel Prize in Physics in 1993. The two neutron stars will merge in roughly 300 million years. When they do, they will produce a kilonova, one of the most energetic events in the universe, and forge heavy elements including gold and platinum through a process called rapid neutron capture. Every piece of gold on Earth was probably made in a collision like the one these two stars are slowly falling toward. But here's the detail that lands differently once you sit with it. When LIGO finally detected a binary neutron star merger on the 17th of August 2017, the event called GW170817, it captured the final signal for just over 100 seconds. 100 seconds of data after billions of years of silence. Every binary neutron star system in the universe spends almost its entire life doing nothing detectable. The hole in spiral, the billions of years of falling, is invisible and inaudible. We only hear the last breath. Somewhere right now, hundreds of thousands of binary neutron stars are falling toward each other in complete silence, their orbits shrinking by a few meters per year. We will never know most of them exist. Number 6. In 2019, a team of physicists in the Gran Sasso Mountains of central Italy did something that should probably be more famous than it is. They directly observed the slowest process ever recorded in a laboratory. They watched an atom decay, not a fast decay, not even a slow one by any ordinary definition. The isotope in question was xenon 124, and its half-life, the time it takes for half a sample to decay, is 1.8 times 10 to the power of 22 years. That's 18 sextillion years. Roughly 1 trillion times the current age of the universe. Across the entire lifespan of everything that has ever existed, xenon 124 is essentially immortal. And yet, in 1 year of observation, the team detected 126 of these decay events. The reason they could do this at all is that they had a detector containing 3.2 metric tons of liquid xenon, buried 1.5 kilometers underground to block cosmic rays, and running around the clock. It was a dark matter detector. The Xenon 1T experiment. Finding the Xenon 124 half-life wasn't the goal. It was a side effect, a bonus. An accidental record set by an experiment that had, in its primary mission, found nothing. The machine built to find dark matter, which may or may not exist, instead set the record for the longest process ever directly observed by humanity. And it did it by catching 126 atoms making a decision they only make, on average, once every 18 sextillion years. Physics rewards patience in strange ways. Number 5. Here is a thing that was considered settled science for a long time. The Milky Way and the Andromeda galaxy are on a collision course. Andromeda is currently about 2.5 million light-years away and closing at roughly 110 kilometers per second. Models built from Hubble Space Telescope data in 2012 concluded with apparent confidence that the two galaxies would begin to merge in approximately 4 billion years and complete their merger roughly 3 billion years after that. A slow-motion collision spanning a total of 7 billion years. Galaxies don't collide the way objects collide. The stars inside them are so far apart that almost none of them will actually hit each other. What happens is more like two clouds of glitter passing through each other, except gravity reshapes everything in the process. The night sky would transform. New stars would form in the turbulence. The Milky Way's distinctive spiral arms would be torn apart and rebuilt into something else entirely. The resulting object, sometimes called Milkomeda, would likely be an elliptical galaxy, a featureless ball of stars, the kind the universe eventually makes when two spirals are done fighting. But here's what changed. In 2025, a team led by astronomer Til Sawala published a paper in Nature Astronomy using data from the Gaia Space Telescope, a far more precise dataset than anything available in 2012, and found that the collision is not, in fact, guaranteed. Their models, running the gravitational interactions between the Milky Way, Andromeda, the Triangulum Galaxy, and the Large Magellanic Cloud, found the outcome to be roughly a coin flip. In roughly half of the simulations, the two galaxies pass close to each other, but don't merge. Not within the next 10 billion years, anyway. What changed the calculation? The Large Magellanic Cloud, a dwarf galaxy, a companion to the Milky Way, about 1/100th its mass. It wasn't properly accounted for in the earlier models because Gaia hadn't yet given us the data to understand its velocity and orbit precisely enough. One small, irregular galaxy, hanging off the edge of our own, may be enough to redirect the trajectory of two giants containing hundreds of billions of stars each. We thought we knew our galaxy's fate. We had announced it, we had made visualizations of it, and then a better ruler came along, and it turned out we didn't. We still don't. Number 4. Somewhere in you right now, in your bones, your blood, the atoms of the chair you're sitting on, there are protons. There are protons in everything. And for most of the history of physics, protons were considered perfectly stable, immortal, permanent fixtures of reality. Then grand unified theories came along, a class of theoretical frameworks that attempt to unify 3 of the 4 fundamental forces of nature: electromagnetism and the 2 nuclear forces. Many of these theories predict that protons should eventually decay. Not quickly, but eventually. After something like 10 to the 34th years or more, a proton should, in theory, spontaneously disintegrate into lighter particles. To test this, Japanese physicists built Super Kamiokande, a cylindrical tank buried 1,000 meters underground in the Kamioka mine in Gifu Prefecture, filled with 50,000 tons of ultra-pure water and lined with about 11,000 photomultiplier tubes, each one watching for a tiny flash of Cherenkov radiation that would signal a proton's final moment. The experiment began collecting data on the 1st of April, 1996. It has been watching ever since. No proton has ever been observed decaying, not one. The current lower limit, the minimum lifetime a proton must have based on the absence of any detected decays, stands at greater than 2.4 times 10 to the 34th years. That's for the most likely predicted decay mode. Some channels push the limits even higher. Every year, Super Kamiokande runs without seeing a decay. That lower limit gets a little longer. Here's the thing though. 2 Nobel Prizes in physics have been awarded for discoveries made using Super Kamiokande. In 2002, Masatoshi Koshiba won for detecting cosmic neutrinos. In 2015, Takaaki Kajita won for discovering that neutrinos have mass, which required neutrino oscillations, which were found using Super K data. The biggest ongoing experimental failure in particle physics has produced 2 Nobel Prizes. The machine keeps failing at its job and keeps accidentally changing our understanding of the universe in the process. The protons in your body may be immortal, or they may have a lifetime so long it makes the age of the universe look like a Tuesday afternoon. We genuinely do not know which. And there is a very large, very expensive tank in Japan that has been watching them for nearly 30 years, hoping to find out. It is still watching. Number 3. Picture the far future, not the near far future, not a million years or a billion. Much further, 100 trillion years from now, the last red dwarf has finally burned out. Star formation ended long ago. Black holes have been slowly evaporating for aeons. The universe is cold and dark and, by any reasonable measure, finished. Physicist Matt Kaplan sat down and asked, "Is there anything left?" And the answer he found, published in the monthly notices of the Royal Astronomical Society in 2020, is that yes, there is one more thing. There is one more type of explosion the universe has not yet produced, and it will happen, is, in fact, guaranteed to happen, at a timescale so obscene that the number itself resists being written down. Here's how it works. When a star like our sun dies, it leaves behind a white dwarf, a dense, cooling remnant made mostly of carbon and oxygen. Over trillions of years, white dwarfs cool completely and go dark, becoming what are called black dwarfs. But even in that frozen state, something is still happening. Pyknonuclear reactions. Fusion reactions that occur not because of heat, but because of extreme quantum pressure, are still, very slowly, converting matter into iron. One reaction per million years. One reaction per billion years. Slower and slower, but never quite zero. After enough time, the most massive black dwarfs, those between 1.2 and 1.4 times the mass of the Sun, accumulate iron cores dense enough to trigger collapse. And when that happens, they explode. A supernova. In a universe that has been dark and silent for longer than any number you've ever used in any context. The first of these black dwarf supernovae will occur in roughly 10 to the 1,100th years. The last, the absolute final supernova the universe will ever produce, happens at around 10 to the 32,000th years. That second number is what Kaplan himself described as the largest number I'll probably ever use in any serious calculation in my career. He also noted, in the most understated way possible, that he had no real way of picturing it. Writing that number out, digit by digit, would fill a short book. But the number is not the thing that stays with you. This is, by the time those supernovae occur, galaxies will have dispersed. Black holes will have evaporated. The expansion of the universe will have carried every object so far from every other object that nothing will ever interact again. Each black dwarf will be alone in a way that doesn't really have a word. And when it explodes, when it produces the last flash of light the universe will ever generate, there will be no one to see it. No detector, no observer, no other matter anywhere close enough to catch the photons. Every one of the last supernovae will occur in complete, lightless solitude, an ending with no audience, not even the universe watching itself go out. Number 2. Stephen Hawking announced in 1974 that black holes are not eternal. That's not the counterintuitive part. We expect things to eventually end. The counterintuitive part is how. Hawking showed, using quantum field theory applied to curved spacetime, that the area just outside a black hole's event horizon constantly produces pairs of particles. One falls in, one escapes. And that over time, this process causes the black hole to slowly lose mass. The radiation emitted is called Hawking radiation, and it means that every black hole in the universe is, technically, dying. A stellar mass black hole, say 10 times the mass of our sun, has an evaporation timescale of roughly 10 to the 67th years. A supermassive black hole, 100 billion times the mass of the sun, takes upwards of 10 to the 100th years. A Google years. That's a 1 followed by 100 zeros, just to evaporate. But here's the part that doesn't get said enough. Right now, today, no stellar black hole is actually losing any mass. Not a single one. Because Hawking radiation temperature is inversely proportional to mass. The more massive the black hole, the colder it runs. A 1 solar mass black hole radiates at about 61.7 nanokelvin. The cosmic microwave background, the ambient temperature of the universe, is 2.725 Kelvin. Every stellar mass black hole in the universe is currently colder than the background radiation it sits in, which means it's absorbing more energy than it emits. The clock on black hole evaporation hasn't started yet. It won't start until the universe cools to match the temperature of a given black hole. For stellar mass black holes, that's roughly 10 to the 19th years from now. So, black holes will eventually evaporate, and not a single one has begun the process. And here's the other part. Hawking radiation has never been observed in any astrophysical black hole. Not once. The temperatures involved are far too low to detect with any instrument we've ever built or are likely to build. We believe it's real because the theoretical derivation is solid. Multiple independent approaches to quantum gravity all arrive at the same answer. But empirically, directly, we have zero confirmation. We are certain, at a theoretical level, that the most destructive objects in the universe are dying, and we cannot prove it. Somewhere between theory and observation, there is a gap. And in that gap, 10 to the 100th years of physics is quietly waiting to happen. Number 1. In the late 1990s, physicist Don Page at the University of Alberta sat down with the machinery of statistical mechanics and asked a very specific question. If you treat the observable universe as a closed physical system with a finite number of quantum states, how long does it take for that system to return to a configuration approximately like the one it's in right now? The answer he arrived at was not a number you can write in standard notation. It requires stacked exponents, a power of a power of a power of a power. The Poincare recurrence time for a black hole with the mass of the observable universe is approximately 10 to the power of 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 2.08 years. Page described this with measured understatement as the longest finite time he believed had ever been explicitly calculated by any physicist. For scale, everything else on this list, the red dwarf stars burning for 10 trillion years, the black hole taking 10 to the 100th years to evaporate, the last black dwarf supernova at 10 to the 32,000th years. All of those numbers are not just smaller than the Poincare recurrence time. They are, for all practical purposes, zero. They don't register. The recurrence time doesn't begin where the black hole era ends. It begins somewhere so far past the end of everything that past the end of everything doesn't capture it. This comes from a theorem proved by Henri Poincare in 1890. Any physical system that is bounded and has a finite number of states will, given enough time, return arbitrarily close to its initial state. It's not a guess. It follows from the mathematics. The question is whether the universe actually satisfies those conditions, whether it's truly bounded, whether quantum states are truly finite. We don't know. The theorem is airtight. The application to cosmology is uncertain. But here's the thing that makes this item different from everything else on this list. Every other timescale here is about events happening in time. Something forming, something falling, something exploding, something evaporating. The Poincare recurrence time is about something else entirely. It's about whether time itself has a kind of structure we can't perceive from inside it. Whether the universe, given long enough, cycles back through arrangements it has visited before. Not because someone resets it, not because of any external cause, just because there are only so many ways matter and energy can be arranged, and eventually, by sheer probability, everything repeats. But even if that's true, even if, after a number of years that requires stacked exponents to write, the universe's quantum state returns to something like this moment, there would be nothing to experience it. Every structure, every pattern, every memory, every observer would have dissolved and reformed and dissolved again, countless times before the cycle completed. The recurrence would have no witness. It wouldn't feel like anything. It wouldn't mean anything to anyone inside it, because there wouldn't be anyone inside it. There would just be the same configuration, again, with no record of having been here before, and no awareness that it was happening. Which means that what makes this moment, right now, you watching this, these atoms arranged in this specific way, what makes it significant is not that it's the first time this configuration has existed. It might not be. What makes it significant is that, for an observer inside it, it is the only one that will ever feel like now. That framing doesn't come with a clean resolution. It's not comforting, exactly. It's not frightening, exactly. It's something else. It's what happens when you follow the physics far enough that the numbers stop being about the universe and start being about what it means to exist inside one. The universe has been here for 13.8 billion years. By every measure we've looked at today, it is still very early. Whatever is coming, the trillion-year stars, the silent supernovae, the slow evaporation of black holes, the impossible recursion of recurrence time, most of it is still ahead. Astronomically, literally, stubbornly ahead. And none of it needs us to understand it in order to happen. But we keep trying to understand it anyway. We build detectors in mountains to watch atoms not decay. We point telescopes at the sky and time a planet's last orbit to within 29 milliseconds. We write papers containing numbers too large to write out, and then write them out anyway. That impulse to measure the unmeasurable, to look at the edge of comprehension and keep walking, that's not nothing. That might be the only timescale in this video that belongs specifically to us. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.